Okay, so today is when things start to get interesting. We've already introduced the idea of basic vectors, that they have two components. They have magnitude as well as direction, and depending on what type of vector, whether you're talking 2 dimensions or 3 dimensions, in 2 dimensions they have vectors or a direction that goes 360 degrees. And we will look at 3 dimensional vectors soon. But we looked at some basic operations, adding vectors, setting them tip to tail. We can use, if we're just talking about vectors in the real world, we could use trigonometry to determine the new magnitude of the resultant vector, whether they're right angle or not. We looked at a right angle example, but you could use any example because we have the cosine law and sine law. And as long as you have the bearing of the vectors as well as their magnitude, you could always determine the resultant. Not something that we do a lot of in this course because it's just not a great system to do anything too powerful. But in the real world, that could certainly be something that you might do, something useful. And, you could find the magnitude of the resultant vector as well as the direction, right? You could find the angle by setting them tip to tail or whatever it is. We talked about multiplying by a scalar. We talked about some of those other operations as well, subtracting vectors. Then we talked about Cartesian vectors, much more powerful, much more useful way of representing vectors from a mathematics perspective. And we looked at the same operations with them, scalar multiplication, as well as determining new vectors, a vector between 2 points P and Q. As I said, turns out that's a fairly important concept and something that we just tend to use from time to time, and so it's something that you really want to know. But today we get into we sort of start scratching the real surface of operations that don't have an equivalent in our mathematical background. So this is very new. The dot product is one of the products that we're going to look at. And so it's not intuitive, as adding vectors or multiplying by a scalar. I think it has some intuition built into it, but this one does not. And this is where we start to see, I think, get a better glimpse of how vectors are different from numbers that we've been using previously. So the first thing I just want to point out is there are actually 3 different products involving vectors. Okay, so we've already seen multiply by a scalar. Today we're looking at dot product, and in a couple of days we're going to look at the cross product. And the dot product and cross product are very different. So let's talk about this a little bit first. So when you multiply scalar multiplication, when you multiply a vector by a scalar, what do you get? What's the result? Not specifically, but the result is a vector. We talked about this at the time, but without the same context, I don't think it's as obvious how important it is to understand what the result is when you do any of these different kinds of products or multiplication. Okay. So now we're going to define the dot product, then we're going to talk about it a little bit. So you've given 2 vectors, vector A and vector B. A dot B, vector A dot vector B, is equal to the magnitude of A times the magnitude of B times the cosine of theta. What is theta? Theta is always defined as the angle between A and B when they are set tail to tail. So if I have 2 vectors A and B, I'm going to try to draw this nicely. I set them up tail to tail, and theta will always be the angle between them, just like that. Okay? And I will no longer define theta. Theta will not always be defined as the angle between A and B when they are tail to tail in different questions on, homework quizzes, tests, whatever. Whenever you're said find theta, it's implied that that's what theta is. It's implied that theta is the angle between the 2 vectors when they're tail to tail. and unless otherwise stated, of course, but this is a standard, so we're going to use theta as having that meaning. Okay, so something to think about is, what is the magnitude of A? The magnitude of A, not specifically, we don't even know what A is, whether it's Cartesian or not. The magnitude of A is just a number, right? Magnitude removes direction and is just a number. It's always positive. If it's directional in the negative sense, then in a particular question you may have a negative, but the magnitude of any vector is by definition positive. It's just a number, so maybe it's 5. What about the magnitude of B? Well, same thing. It's just a number, so maybe it's 8. What's cosine of theta? And this is something that we lose track of when we do trigonometry. We forget what it actually means. It's a ratio, but a ratio, a fraction, is just a number. Okay, and cosine of theta is always between 1 and -1, so it's some decimal number between 1 and -1, but ultimately it's just a number. So I'm multiplying 3 things that are all just numbers. So that means the product of 3 numbers is just a number, and that means the result of the dot product is a scalar. It is not a vector. It's not like when you're multiplying a scalar by a vector and you get a vector as the result. When you take the dot product of 2 vectors, your result is a scalar. This is an important idea, that we understand all the different kinds of operations and what the result is. In fact, we're going to do different questions and activities to practice just thinking about what the result would be in the general sense, not in specific cases. And I think that's an important exercise to go through. So take the dot product of 2 things, then the result is a scalar. Before we start talking about what the dot product is, I want to look at a few examples of this to highlight what I mean by how important it is to understand these operations and their result. What if I have something like this? So A dot B plus C. At first glance, it looks perfectly fine, but think about this. What does this mean? This looks like the math that we're very familiar with. It just looks like you do variable A times variable B and add variable C, and that's something that we could do if those were variables. But these are vectors. So what does it mean to take the dot product? Because this is in brackets, so I have to do that first. So what does it mean to take the dot product of 2 vectors? Well, that gives me a scalar. Well, what does it mean to add a scalar to a vector? It doesn't mean anything. It's nonsense. So this operation is undefined. It has no meaning whatsoever. And this is the problem that we get into when we first start learning, in particular when we first start learning about vectors, is that you get these expressions that look perfectly meaningful, but they actually don't have any meaning. Okay, and again, so this is an exercise that we're going to talk about. This is and explore further. Let's try another one. So what's going to be the result of this? Well, A dot B, again, gives me a scalar. So this ends up being a scalar times a vector. And that's a vector. So that one is perfectly fine. What about this one? This is a vector times a vector. This seems reasonable, but in fact, this is also undefined. Because we have 3 different types of products. And this one, which is the product of 2 vectors, but it's not a defined product, right? If you have a scalar times a vector like we did there, then you have a defined operation for multiplication, and you just multiply each component of the vector by that scalar. That's defined. So that type of just general multiplication has a definition. But general multiplication, which is what this is because it's just brackets beside brackets, has no definition with vectors. if you're taking the product of two vectors, you have to say, is it the dot product or is it the cross product? I can't simplify a dot B to a bracket B because this is not a product that has a definition. I have to leave it as the dot product, or when we get to it, as the cross product, which for future reference looks like that. So it uses the X multiplication symbol, and it's like a cross, obviously. So that's what the cross product is. So again, I cannot, and the cross product is very different from the dot product. They're totally different operations. So I can't simplify A dot B to A times B with an X. Like, that doesn't make any sense. It's changing the operation entirely. So this is something that's quite new, where when you have two numbers, you just multiply them. And, if you think back, ultimately, what is the definition of multiplication? A simple way of looking at it is grouped adding. I'm taking a group of something multiple times. So 3 times 5 is, I have 3 groups of 5 or 5 groups of 3, however you look at it, but it's the same idea. And so I'm just have a group of something multiple times. And that's what multiplication is. But with vectors, that has no meaning. That same idea operation of multiplication doesn't have any meaning. You might say to yourself, why can't I just multiply the x's, multiply the y's, and multiply the z's, right? Why doesn't vector A times vector B just mean that? So if I have vector A, which is 2, 3 times, so just beside another bracket, times 4, 5, why doesn't that just mean 2 times 4 is 8, 3 times 5 is 15? Well, you could define this operation this way if you wanted to. That's something that you could do. That's something that mathematicians could do. That could be a worldwide, a common definition of, quote, multiplying vectors. The problem is, what does this mean? What value does it have to do this? What's the purpose of doing this? What's the implication of doing this? The result has no value, at least none that I know of. It has no importance, no usefulness. So there's no reason to define an operation this way. General multiplication of integers has a great value. We've seen it tons of times. If I'm buying a bag of apples and there's 10 apples per bag and I buy 5 bags, now I know I have 50 apples. Like, that just has inherent value. It has something that we can understand and something that we can use. Turns out that idea of vector multiplication doesn't really have any use or value. So we have these two other products where now multiplying a scalar by a product is more similar to that idea, that I have a vector and that if I want to take 3 of them, now I have a vector that's 3 times as long that's in the same direction, right? So that's closer to the idea of just multiplying 2 integers together, is multiplying a vector by a scalar. But we have these two other products, 2 other operations, dot product, cross product, and they both have very different meanings and outcomes. And so this is kind of what we're getting used to for most of the rest of this unit. And some of the outcomes are very simple, straightforward, but very powerful, surprisingly powerful. And then some of the other implications of these things are stuff that we're not going to have time to get into, and you would have to look at real world applications of vectors to further understand what the meaning or value of this is. Okay? So if you actually applied it in a physics class, then you would start to see, in this case, the dot product has this meaning. I'm going to try to give you a couple of ideas that may or may not be overly satisfying. Okay, so just generally, what is the dot product? The dot product is when you project one vector onto another, okay, and then you multiply those magnitudes. So if you think about what it means to project something onto something else, as if you had a light source and you were projecting an image or a shadow onto a wall or onto another object. Okay, so let me draw a diagram. This is vector B. This is vector A. So A dot B, here's the angle between them, so we're going to define that as theta. A dot B means my light source is directly above, and I'm shining or projecting a shadow of A onto B, which gives me not a vector, but a length C, which is this length. And we can see that this is now a right triangle. Okay. And then I take the length of C, multiply it by the magnitude of B, and that's what gives me the resultant dot product. So a couple of ways that we can look at this again if we're looking at the formula to try to make sense of it. First of all, cos of theta is adjacent over opposite, which is C over the magnitude of A, right? Because we're only talking about lengths here, which means C is equal to the magnitude of A times the cosine of theta, just rearranging that. Okay, but I already said that A dot B is the multiplication of the magnitude of the projection of A onto B, which in this case is C, times the magnitude of B. So A dot B equals C times B. Now, again, I just finished this whole big thing about how you can't just multiply two vectors together, but neither of these are vectors. C is a value, it's just a length, and the magnitude of B is also just a length. But then I can say, well, what is C? It's the magnitude of A times the cos of theta times, and then I multiply times the magnitude of B. So just replacing C with that, okay? And rearranging this, I get that formula that we saw. That is the formula for dot product of two given vectors where you're given their magnitudes. Again, this is not Cartesian stuff yet. We're going to look at that. But if you're just given their magnitudes and given the angle between them, then you could find the dot product of those two. And it has to, and it's hard to understand. It's really difficult. I'm going to give you one good example and two maybe not so good examples. Unless you were exploring this further in an engineering course or a physics course, but that is what it is. It is the projection of one vector onto another, which again gives you a length, and then you take that length, multiply it by the length of the vector that it projected onto, and you either get a longer magnitude or shorter magnitude than this vector that you started with, and that's what the dot product means. There's one really good implication of the dot product, which we will talk about today and see today. And if that's the one thing that you take away other than the formulas of how to do this, then that's a pretty good idea. So don't get hung up too much on the bigger picture of what the dot product means. Because in this course, we're not really going to have to get into it. Here's my three examples. Mechanical work, this is a definition in engineering or physics, is the dot product of force and displacement vectors. In fact, I think some people who have a good understanding of physics, if you've taken for you physics, you may actually be able to think about what that means. Displacement vectors and force along those vectors or across those vectors gives you the mechanical work that's involved in the situation. Mechanical work doesn't have to have a direction. It could be along either of the vectors. But if you're talking about a particular object in the direction it's moving, you would talk about the work on that object in the direction that the object's going. So you could take the direction of the dot product and sort of apply it in different directions, whatever direction you want. And that's why it doesn't have an inherent direction itself. Okay, I don't want to get too much into that, but those of you who have taken physics, that one might be satisfying to you. You might be able to understand what's happening there. And you could even look back at some examples that you've done where you're finding force in a particular direction or the amount of work in a particular direction, and realize that the formula you use in physics is same or similar to that formula. This one might be simplified. I'm not sure. Apparently, magnetic flux is the dot product of the magnetic field and the vector area. So if you were studying magnetical fields, the physics of magnetical fields, or in an engineering perspective, again, I think that would make sense to you. It doesn't make a lot of sense to me, quite frankly, but this is one of the real world applications of the dot product that I was able to find. Here's the best one, I think. If you've ever played Mario Kart, I think this is maybe the best example of the dot product, just for your understanding. Now, there are going to be people who are going to argue and tell me this isn't actually how the Mario Kart booster pads work, and that's fine. I don't really care. I'm not convinced that it's not how they work, but I haven't been able to either confirm or not confirm that this is how they work. I've played a little bit of Mario Kart, but I've not done any testing, so I don't know for sure. The whole point here is, let's say you are in your kart and you go over the jump pad directly. If it was true that your resultant velocity, so not your direction, but just the velocity, just your overall speed, is the dot product of your vector as you go over the boost pad. If you've never played, this is called the boost pad. And when you go over it, you get a boost of speed for a short amount of time. Okay, that's essentially all that it does. And so if I go over it directly, okay, then my velocity going into it is added to the multiplier of the boost, whatever that is, and I get a boost of speed. In this case, that would be kind of maximized. But what if I go over it at an angle? So if it were true that it used the dot product to determine your boost, then it would take the difference of the angle between the boost pad in its sort of forward position and the angle that you cross it, and you wouldn't get the maximum possible boost. Your boost would be in the direction that you are going. It's not going to launch you sideways. It launches you further, increases your speed in the direction that you're going, but you wouldn't get as big a boost. And if you went over it at a right angle using the dot product, you would get no boost. Okay. So that's to me a good way is that the more closer to running over a boost pad directly, the larger your boost is going to be. And if you run over it perfectly in line with its direction, you would get the maximum boost. But as you decrease or increase that angle from straight, and your angle becomes more sideways across the boost pad, you wouldn't get as much of a boost in the direction that you're going to. Again, I'm not saying that this is actually how it works, but I think it's the best example of what the dot product is actually talking about. One way or another, that's not something we want to get hung up on right now, because we are really just getting used to using the dot product and working with it and that kind of thing in a mathematical sense. So let's do a few examples here. Determine each dot product. So again, I'm given the magnitudes of two vectors. You can see that vector B is longer than vector A. They're probably relatively speaking to scale, but not perfectly. And you're given the angle between them. So that means that A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them, which is 30 times 40 times cos of 50. Literally just punching it into your calculator, you get 771.3. And units of whatever you're talking about, force or whatever, or work or whatever it is you're talking about. We don't really have a lot of units for this. We don't worry too much about it. Okay, but that's what it would work out to. So, and again, it doesn't have a direction. It could be a long A, it could be a long B. I think that's more of an application thing. Like It's more contextual to what you're talking about, the work in the direction of the object that you're pushing, something along those lines. Okay, but it's just using a simple formula, punching in some values, pretty straightforward. You need to know the formula, obviously, but that's the way that this works. One note before we move on, if you're trying this on your calculator, depending on what you've been doing most recently, recognize that your calculator has to be in degrees, which we did talk about at one point, but this is an important idea because when we do the exam for this course, a whole bunch of work is going to be done in radians, and then some of the work is going to be done in degrees. So you have to know when to switch, which will make it clear on the exam when you should switch. But you just know if you're working with vectors, you should be always in degrees. And if you're working with other trigonometry, you should be in radians. Okay, let's take a look at another one. So vector u dot vector v is magnitude of u times the magnitude of v times the cosine of the angle between them, which is 112 times 125 times cosine of 135. And if I just punch this into my calculator, I get negative 9,899.5. Now that's interesting. Why do I get a negative? Well, obviously these forces or whatever they are acting against each other because they're not going opposite of each other, but they are going opposite-ish, and so they're having a negative impact on each other. And where does the negative come from? Well, if I take the cosine, am I in degrees here? I think I probably am, of 135, I get a negative, right? So that's where the negative dot product result comes from. It comes from the negative in the cosine of an obtuse angle. Okay, so that will work itself out. You don't need to know, but if they're going opposite-ish directions from each other, you're going to get a negative. That's something that's good to expect. Okay, last one here, vector m dot vector n is, the magnitude of m times the magnitude of n times cosine of the angle between them. Well, what's cosine of the angle between them in this case? It's 90. And what happens when you put this into your calculator? Oh my gosh, you get 0. Does that make any sense? Well, it actually does. If we can use our understanding of cos of 90 or cos of pi by 2, we know that that value is 0. So that's what gives us the 0. And it turns out, again, this is really important. This is the thing I've been sort of alluding to, one of the most useful for us results of the dot product, that two vectors that are perpendicular to each other will have a dot product of 0. So if I wanted to determine if two vectors were perpendicular to each other, I could take their dot product. If it's 0, they are perpendicular. If it's not 0, they are not perpendicular. Okay, so this is a just for us and the kinds of stuff that we do. It turns out that this is a useful idea, so it's a good one to remember. Okay, but again, the cos of 90 is 0, so that makes sense. And this makes sense to that example that I was giving with the Mario Kart, where if you went exactly sort of laterally across or perpendicular across the pad, you would get no boost at all. I don't think that's actually true about how the game works, but it would be interesting to use the dot product to calculate that boost, and then in that case, that's what would happen. Okay, some properties of the dot product. So every one of the different operations that we're going to do, dot product, cross product, multiplying by a vector, adding vectors, all of that stuff has different properties. Okay, we already talked about this one. So I'm just going to write it down. A dot B equals 0 if and only if, so this goes both directions. If it's 0, then this is true. If this is true, then the dot product will be 0. So it's a very useful idea if A and B are perpendicular. Okay, not parallel, not collinear. The opposite of that, which is, or I don't know if it's opposite, but the other version of that, which is perpendicular. They're at a right angle to each other. Okay. A dot B, here's our formula. Well, these are just numbers, and A times B or one number times another number is the same whether I do it one direction or another. So this is true for this as well. Okay. The magnitude of A times the magnitude of B is the same as the magnitude of B times the magnitude of A. 2 times 3 is equal to 3 times 2. And if I write it this way, it's subtle, but I guess this means B dot A, right? And this is important because not all operations with vectors hold this property. So A dot B is the same as B dot A. Order doesn't matter. What about vector A dot vector A? Interesting. Okay, so magnitude of A times the magnitude of A times cosine of the angle between them, which in this case would be 0. What's a cosine of angle 0? Where does the cosine graph start? Starts at 1. So this is magnitude of A times the magnitude of A times 1, which is the magnitude of A squared. Okay, A dot B plus C, it's true that it holds that distributive property, so that is equal to A dot B plus A dot C. This doesn't always have to be true. I talked about this before. Distributive property holds for some things, not others, but for the dot property, it does hold. So the dot product is distributive. And some constant, some scalar, K, times bracket A dot B is equal to the same scalar K times vector A, so that's scalar multiplication, dot B. Okay, so this is what we call associative. So the dot product is also associative with multiplication of a scalar. And these are things that you kind of want to just try to remember the different properties for the different operations. Okay, we'll do a little bit of practice to try to get used to that. So how could I simplify this idea? Well, I could take Ku dot U and Ku dot V because it's distributive. So this is K times U dot U plus Ku dot V. Now I wrote the first one that way for a reason, because then I can simplify this as K times the magnitude of U squared, because that's what this is going to work out to. And then the order in which you do this really doesn't matter, but whoops, just showing that both are equal. Writing it this way and then writing it this way doesn't matter. Order has no meaning. There's no reason why I did it one way or the other, but I wanted to show that they're equal, and I wanted to show that you could simplify that one that way. Okay, what about this one? Well, again, distributive property holds. So subtracting two vectors gives me a vector. Adding two vectors gives me a vector. I can take the dot product of two vectors, and that also means that I can use binomial distribution to simplify this. It will work as well. So this is equal to U dot U plus U dot V minus V dot U, but we already said that they're associative, so U dot V and V dot U are the same, minus V dot V. So these add to 0, and this ends up being the magnitude of U squared minus the magnitude of V squared. And this isn't something that's going to come up a lot, so this isn't a useful thing to memorize, but it does show you, some of, like if you were doing more and more and more with vectors, there are some of these ideas would definitely become useful to understand. And that's similar to binomial expansion that we've done. A plus B times A minus B gives you a difference of squares. That's the same kind of thing. And some of these things are going to be true for vectors, but sometimes they're not. And the different operations with vectors, dot product compared to cross product, is not always going to be the same things that are true. Okay. Now here's where, again, like I said last day, Cartesian vectors are more powerful for us, but it's important to just think about vectors in general. So that's why we always do talk about it that way. But this is going to be more useful. So let's look at the dot product for Cartesian vectors. We're going to derive this formula. Okay. First of all, I'm going to define, if I have two vectors, A and B, they're tail to tail, and theta is the angle between them, I can define vector C, as the vector from the tip of B to the tip of A. And this means that B plus C is A, right? If now B and C are tip to tail, so B plus C is A. So that's the first definition I'm going to write out. B plus C is vector A. And this is going to be useful later. That means C is vector A minus vector B. I'm also going to define vector A as AX, AY. I'm going to define vector B as BX, BY. And that means vector C, is equal to, we've already done subtracting vectors, Cartesian vectors. So if it's A minus B, it's AX minus BX, comma, AY minus BY. Okay? And so I defined A and B just with general coordinates. I defined vector C and sort of wrote out two different relationships between A, B, and C. And then I used Cartesian vector subtraction to define C in terms of A and B. And there's one other thing I'm going to need for this proof, and that's the magnitude of A. And if we didn't do it now, we would have to do it later. But if you have advanced knowledge of this proof, which after today you will, then you'll know that we're going to need this later. And in fact, we're going to need all the other ones, but I'm just going to write out this one because the other ones are the same. Okay, so don't forget the magnitude of A is the square root of the x value squared plus the y value squared. Okay, now that's the setup. Now we get started, and I'm going to go all the way back again to grade 10 at trigonometry and use the cosine law to define C in a different way. So I've got the magnitude of C squared is the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B times the cosine of the angle between them. And that's just cosine law. A squared plus B squared minus 2AB cos C, or cos theta in this case, the angle between them. Okay? And now I just need to know how to rearrange this in the right steps and sort of sub stuff in or expand stuff in order to get it manipulated into the way that I want it to be. Okay, so I'm going to move the negative 2AB to the left side, and it's going to become positive 2AB cos theta. And I'm going to move the magnitude of C squared to the other side. So I got magnitude of A squared plus magnitude of B squared minus magnitude of C squared. Okay, now I'm going to expand these. I've got an expression for the magnitude of A, and similarly, I can do an expression for the magnitude of B and the magnitude of C. So this is magnitude of A, which is AX squared plus AY squared, all squared. This is the magnitude of A, but it was the magnitude of A squared. Okay, whoops. So that's all squared. Plus, same thing for B, bx squared plus by squared, all squared, minus, this is C. So what's the magnitude of C? Well, it's ax minus bx squared plus ay minus by squared. All of that squared, because those come from here. right? And it's just the x value squared, the x coordinate squared and the y coordinate squared. Well, what happens when you square a square root? They cancel each other. So this ends up being ax squared plus ay squared plus bx squared plus by squared minus, I'm going to do two things here. The square root and the square root are going to cancel out, and I'm going to expand both of those binomial squareds. So this is ax squared minus 2axbx plus bx squared. Hopefully I have room here, yep. Plus ay squared minus 2ayby plus by squared. And we kind of see what happens here. I've got an ax squared minus ax squared gone. I've got an ay squared and an ay squared. Oh, I'm missing brackets. That's why this isn't working. Hold on, sorry. This should be minus all of this. That's better. Okay, so I've got an ay squared minus ay squared. That's gone. Whoops. There we go. I've got a bx squared, and I've got a bx squared here gone, and I've got a by squared and a by squared there gone. So those are all supposed to cancel out, which they only actually do if I have brackets in the correct places. And now I can simplify this to negative, negative, so those cancel. So this is 2axbx plus 2ayby. And this is equal to 2 magnitude of A, magnitude of B, cos theta. And if you look carefully, you probably can figure out what to do. Divide both sides by 2, and I get magnitude of A times magnitude of B times cos theta is equal to ax bx plus ayby. Okay, and what is this? That's our formula for dot product. So that means A dot B equals ax bx plus ayby, and that is our formula for the dot product of vectors A and B in the Cartesian plane. Okay, and so this is a big deal. This is really important. Some simple steps of defining the vectors in a particular way, setting them up in a particular way, and then just using cosine law and expanding and sort of subbing in and expanding, dividing by 2, and we notice that this is the dot product. So just to recap one more time, if A, I'm going to actually write this in a different way, is A1, A2, and B is B1, B2, or BX, BY, same thing, then A dot B in vector space is equal to A1, B1 plus A2, B2. This is a formula that you absolutely need to know and memorize, and it's really important, and you notice that you multiply the x's and multiply the y's. Kind of like you might have been thinking about before, about isn't that just what you would do, okay? But it doesn't give you a vector. So it gives you a scalar. Dot product result is a scalar because this is two numbers multiplied, added together, just gives you a number, not a vector, okay? Okay, so last thing, we're gonna just do a couple of quick examples with this. So u dot v, this is in Cartesian space. 4 times 5, so I multiplied the x's, plus negative 2 times 3, whoops, getting ahead of myself there, multiplied the y's, 4 times 5 is 20, negative 2 times 3 is negative 6, so this is 14. Again, whatever that means, Depends on the application, but it's a scalar. It's just the number, not a vector, so I can't then add it to a vector or anything like that, like we talked about. And there's a simple example of the dot product. You can really see how Cartesian vectors are better. They're easier to use. They're better to work with. They're more meaningful in a lot of ways. They're very straightforward. Okay, last example. Given two vectors A and B, find A dot B. So 6 times 1 plus 3 times -2 is 6 minus 6, which is 0. What does that mean? What we talked about this? Well, let me draw out these two vectors. 6, 3 is this vector here. Okay. And 1, -2 is this vector here. And it sure looks like they are at right angles to each other. And if you thought of those as lines and thought of them as a slope of lines, you could convince yourself that they are perpendicular to each other, because this one's going up 1 over 2, up 1 over 2, and this one's going down 2 over 1, down 2 over 1. And so they are the negative reciprocal to each other. They are at a right angle, but the dot product also shows us that. And if I ever get a dot product of 0, it definitely means that they are perpendicular to each other. And if they are perpendicular to each other, then their dot product will be 0. So that's the lesson on dot product, both in just general space and then in Cartesian space. You need to know both those formulas. You need to know that last application that we looked at in example 4. And that's about that. Dot product, one of 3 different types of products we can take involving vectors. We've seen multiplying by a scalar already. Now we've seen dot product. Okay, and we will in a couple of days look at cross product, but cross product has its own unique idea that we have to spend a day doing something else on before we can get to it. So that is the dot product.